I'm Baojun from Tsinghua University. Thanks for joining us in this talk. Today, we are going to talk about a threat in DNS, the hidden interception of the DNS resolution path. We are focused on how it works and perform a measurement study of this hidden behavior. Some previous studies show that ISP DNS resolver might have security problems. As a solution, Internet users often trust popular public DNS resolvers because they are good services and security, such as Google Public DNS. However, have you ever imagined when you use Google DNS as your resolver, your query may be answered by someone else? What if your DNS request gets intercepted on the way and handled by other resolvers that you don't even know? What's worse, when they give you the responses, they pretend to be Google and make you trust them. So this is what we call hidden DNS interception. Requests are intercepted on the way, and IP spoofing is performed for make-believe. Next, who would potentially intercept our DNS queries? We can firstly think of Internet service provider. Their mailbox in the network are able for modeling. Besides, other devices such as firewall, antivirus software, and enterprise proxy are also potential interceptors. For example, AWS software provides a default functionality named Secure DNS. This functionality makes AWS redirect all DNS requests from client-side to AWS DNS server in an equipped channel. Until now, we still do not comprehensively understand this kind of hidden threat. So to study this threat in our work, we merely want to answer two questions. The first one, how to globally measure the hidden DNS interception. And the second one, what are the characteristics of this hidden behavior? Okay, now let's take a look at the threat model. We focus on requests to popular public DNS resolvers and discuss how they are intercepted. So normally, when a client chooses to use public DNS resolver, requests will reach at the specified resolver through some unpatched devices. But some devices may manipulate the packets and redirect DNS requests to alternative resolvers, which does the rest of the work and get the response normally. And finally, before the response is sent back, a source IP address is spoofed. So your request to a trusted public DNS have been answered by someone else that you don't know. And it is also quite hard to detect from client side because of IP spoofing. According to our observations, from the view of authoritative name server, we classify the DNS resolution path into 4 categories. The first one is standard normal resolution without interception. A client sends a DNS request to a public DNS, and it only reaches the specified resolver. From the view of name server, it sends only one request from the correct public DNS. The second case is called request redirection. A client sends a request to a public DNS, but it is then redirected to an alternative resolver, not reaching the public DNS. So in this case, the specified public DNS is completely removed from the DNS resolution process, and from the view of name server, it sends only one request from the alternative resolver. The third case, request replication. Same as usual, there's a request to a public DNS. However, this time, the request is replicated. One reaches the correct public DNS, and the other one reaches alternative resolver. From the name server, it will receive 2 identical requests from different IP addresses. Of course, the client will receive 2 responses as well, and typically it will accept the first one. The last case is direct responding. It is similar to request redirection. The alternative resolver handles the DNS query, but it does not really perform a query to the name server and directly return an answer to the client. An incorrect answer, of course. And from the name server, it receives nothing. The next part, how can we detect and measure this hidden interception? Recall that in each of 4 kinds of DNS resolution paths, the authoritative name server sends DNS requests come from different resolvers. So to detect the interception, we send DNS request to specify public DNS resolver from clients and check on authoritative name server where the DNS requests come from. If they are come from the correct public DNS, then there's no interception. Otherwise, if we send the DNS request come from other resolvers, then the DNS request is intercepted on its way. So our method is quite simple at high level. We need to collect large-scale vantage points, generate DNS requests on them, and collect the corresponding DNS request on our name server. However, just like we cannot put an elephant into a real fridge that easy, these three simple steps each poses us to a challenge. The first one, how to collect vantage points. In this study, we need global vantage points. They have to be ethically acquired, large-scale, and diverse. Most importantly, it should allow us to send DNS requests to any IP addresses we want, like Google DNS. In prior studies, in spite of different DNS measurement platforms are developed, they cannot be directly used in our study. For example, JavaScript advertisement network and the Illuminati proxy network only allowed sending DNS requests to fixed local resolvers, so they cannot be used. Okay, to address this challenge, we designed two phases of measurement. The first phase is called global analysis, where we use the proxy rank to collect vantage points. Proxy rank is a VPN model-based socket file residential proxy networks. It allows us to send DNS requests to any IP addresses. When we submit our DNS request to the super proxy, the DNS request will exit from large-scale residential nodes in different countries. Currently, almost all DNS traffic is over UDP, but this network only accepts TCP traffic. So this phase can only describe a big picture of the hidden DNS interception problem. To get more fine-grained data, we design another phase measurement. Here, we implement our measurement scope into a network debugging module of a popular security software. The debugging module is quite similar to Netliner and allows us to generate traffic at socket level, so we can send more diverse DNS packets from these vantage points. Our collected clients are mainly located in China, so this phase is named China-wide analysis. In our study, we take utmost care to protect users' privacy and security. To address ethical issues, we use the following approaches to get granted permission from clients, like a one-time consent and install from user. Also in our study, only DNS queries of our domain are collected without any privacy data. The second challenge is what requests shall we send. To comprehensively understand the characteristics and the interception policies, we should generate DNS requests as diverse as possible. So here are some fields that we suppose the interceptor may consider. Taking one value from each field, a DNS query is generated. Particularly, we consider three famous public DNS resolvers according to their Alex traffic ranking. And we also build a self-owned listener EDO DNS for comparison study. We consider 5 kinds of different DNS resource type and register 4 domain names under different TLDs. To avoid our domain be cached by recursive DNS resolver, we stuff a Unicode prefix into our domain name. Besides, we use a lot of tricks to adjust our experiment, and you may read our paper for details. And now, the third challenge, how to identify egress IP addresses of public DNS. First, I will explain what an egress IP is. In large public DNS resolvers, they often use any cast IP addresses to be reached, like the code 8. However, in the background, loading balancing distributes DNS requests to multiple resolvers, where they use egress IP to talk to our authoritative name server. So from our name server, we need to know if these IP addresses belong to the public DNS. If it is not, then there is an interception. To solve this problem, we leverage the DNS PTR and ISO recorder. The high-level idea is that the DNS recorder can reflect the functionality of the IP addresses that are used by public DNS services. So from each IP addresses that talk to our name server, we first perform its reverse DNS lookup. Then we build its SOA resolution dependence of this responding domain name. If particular second-level domains present in the dependency chain, we regard these IP addresses as the egress IP of the public DNS services. Now, after solving all those challenges, we are able to collect diverse DNS requests from Vantage Points all over the world. Our 100,000 clients are located in more than 170 countries and 3,000 AS numbers. Due to the timing limitations in the rest of this talk, I will use the result that we collected by our debugging tool for the DNS interception analysis. Finally, here are some results of our interception analysis. We are focused on characteristics of the DNS interception and influences on DNS lookup performance. Also, we perform analysis on the DNS response manipulation and security threats. Finally, we discuss the potential motivations behind the DNS interception and any solutions. First is the landscape of DNS interception. In total, 259 AS that we inspect existing DNS interception behavior. When we classify the intercepted request by kind, we find that direct responding is rarely exist. This is because the response is clearly incorrect and it is easy to identify. Also, request redirection is much preferred than request replication. Break down to different reservoirs. We find requests to well-known public DNS services are more likely to be intercepted, especially for the Google public DNS. We find in China, up to 28% requests over UDP from clients are intercepted. By contrast, only 10% of DNS requests to the least popular EDO DNS are intercepted. Zooming to the top AS with most of our DNS queries, we conclude that the interception policies can be complex and vary among networks. In all these 4 AS, rate of request redirection is higher than request replication, especially for the last AS of China Mobile. Over 45% requests are redirected. However, even between 2 AS of the China Mobile, the interception policies are also quite different, as reflected by the rate of replication. In these AS networks, the alternative reservoir actually located in the same AS as the client. The next question we ask, whether the hidden DNS interception is designed for DNS lookup performance improvement. Here, we use the round-trip time as the indicator of DNS lookup performance. This is a cumulative distribution of round-trip time of DNS request, with each type in different colors. Compared to the green line, which is normal resolution, request replication does receive better performance. However, the request redirection brings uncertain effect. Also, it is quite interesting that the round-trip time distributions of request redirection and directly sending requests to local reservoirs are very similar. Besides, for replicated request, we want to measure whether the original one or the replicated one is fast. So we compare the arrival time at our name server. This graph shows the time differences between the 2 requests in this AS. We can see that in most AS, replicated requests are faster than the counterparts. However, we still find the interesting AS, which is belong to China Telecom Group, with all replicated requests are lag behind. We suppose this can be accounted by the interception devices in this network. Next part, response manipulation. In our datasite, we find hundreds of DNS recorded values are tampered by DNS interception. After manually analysis the tamper response, we find the following classifications, including traffic gateway, illegal traffic monetization, and misconfiguration. For instance, some of our DNS results are tampered by an advertisement web page. This website is belong to China Mobile Group and for promoting a mobile application. Now, of these results, what security threat may DNS interception bring? Definitely ethical concerns. As we mentioned at the beginning, Because of IP spoofing, it is difficult for users to detect interception, so they may not be aware of this kind of hidden behavior. Also, the security of alternative resolver can be problematic. We tested 205 open alternative resolvers that we found, and found only 43 of them accept DNSSEC queries. What's worse, among them, all resolvers that are using Bunch have a software version that should be deprecated before 2009. This makes them vulnerable for various attacks. So, why are they intercepting our DNS queries? We perform a systematic survey on vendors and software platforms that provide this functionality. They first claim that the DNS interception is for improving DNS security. However, we show that the alternative resolver may lack security, and the requests to run no public DNS are more likely to be intercepted. The second motivation they claim it is to improve DNS performance. We show that by replicating DNS requests doesn't improve the DNS lookup performance, but request redirection brings uncertain effect. Finally, Internet service provider would like to reduce traffic exchange among networks. By redirecting DNS traffic, this can be satisfied. After an offline meeting with DNS security team of one large Chinese Internet service provider, this motivation is confirmed. To solve this problem, we believe the key point is to authenticate the resolver that we are using, but its deployment still has a long way to go. Based on our observations, we provide an online checking tool to help Internet users to detect Internet interception. Finally, a brief summary of this talk. By detecting and measuring DNS interceptions, we provide an understanding of this hidden behavior. We collect clients from more than 3,000 AS numbers and find over 250 AS that exist in interception behaviors. Especially, we find in China, up to 28% of DNS requests to Google DNS are intercepted. Also, this behavior brings security concerns. Finally, we discuss the motivation behind the DNS interception and release the online checking tool. In the meantime, we are moving forward the upcoming project and try to identify different kinds of interceptors. Thank you so much for your attention, and I'm happy for any questions.
Hi, Dave Levin, University of Maryland. Nice talk, cool study. You mentioned that you were able to study UDP and TCP. Did you notice a difference in the number of redirected or intercepted?
Yeah, very good questions. In this talk, during the timing limitations, I only chose the UDP, but the TCP we also measured in our paper. The result is that compared to the UDP protocol, the DNS package that over TCP receive much little in DNS interceptions.
Interesting. But it still happened? Or like, were there some ASes that just didn't do any TCP interception, or they just did it less often?
Less often.
Oh, but they still did it.
Okay. Yeah.
Okay.
Yeah,
Thank
for
you.
the details, you may read our paper. Thanks.
Thank you.
Rob Jansen, U.S. Naval Research Lab. I'm wondering, so you use the proxy rack system.
Okay.
I was wondering how many vantage points you had from that.
Sorry?
How many vantage points were available in the proxy rack system?
Millions.
Millions?
Yeah, millions.
Okay, I was going to ask if you considered using RIPE Atlas, because they also have, well, they don't have millions of vantage points, but...
Sorry?
Did you consider using RIPE Atlas?
So can you repeat it?
Did you consider using RIPE Atlas, which is a measurement system that provides vantage points?
Okay. No.
Okay. Thanks.
Hi, thank you for your talk. I have a meta question. Do you think China will allow DNS over HTTPS when that starts getting deployed to solve this?
So sorry, can you repeat it?
Do you think China will allow DNS over HTTPS, the DOE standard?
Oh, very good questions. We have under projects that study this problem. It's hard to say, but we are interested in it. Okay. A good question. Another?
Still have 5 minutes.
Thank you.